Okay, so let's go over some sample midterm questions. Of course, we'll always get the correct one there. So we're going to start and redo these first ones anyway. A student measures the temperature in a room using a digital thermometer. The temperature shows 3 decimal places. The student performs this measurement 5 times, calculates an average, which is this, and a sample standard deviation, which is this. How should the student report this error? Well, the standard deviation should be reported with one significant figure unless it begins with a 1 or a 2, in which case it does. So in this case, it'll be 0.134. Rule 2 says our number has to match. So 32.121. And then the third one rule is, does it make sense? Is this more precise than, let's say, the instrument? In this case, it goes to 3 decimal places, so the instrument of the error in our instrument is in that place, so we're doing worse here. So the answer is B. The student measures the temperature in the room using a digital thermometer. The thermometer shows 3 decimal places. The student performs the measurement 5 times and calculates the average to be 32.212 degrees C. The sample standard deviation as 0.583. How should the student report the result? Well, remember, our standard deviation is reported, rule 1, with 1 sig fig, unless it begins with 1 or 2. This is 1 sig fig, so it's going to have to round. Then we have to, rule 2, this has to match the error. Can't be more accurate than the error. So 32.2. And then lastly, does that make sense? Where is our sig figs from our instrument? Our sig figs is in the 3rd decimal place. This is a lot larger error. So our answer for this one will be E. Okay. A student measures the temperature in the room using a digital thermometer. The thermometer shows 3 decimal places. The student performs this measurement 5 times, blah, 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 right? So 3 decimal places. There's our average. Here's our standard deviation. Rule 1, one number unless it begins with a 1 or 2. It begins with a 1 or 2, so 0.00012, which means this has to match the decimal places, but it can't. So in fact, we're limited right there, so we can't add zeros if it's not in the calculation, or we don't have any information. Maybe if you did the calculation, you would have more. However, we also know that our error, so rule 2, we'd have to say, okay, we have to do something about that because they don't match. But we also know that rule 3 is, does this make sense? And our error will be in this place already. So our answer will be 32.212 plus or minus 0.001, which will be D. Okay. A student measures the temperature in a room, right? Same problem. 3 decimal places, same number. The standard deviation is this. Rule 1, does it begin with a 1 or 2? Yes, so we keep 2, plus or minus 0.0024. This has to match 32.212. It actually can't, remember, because we don't have enough, so this can't be more accurate, so we'd have to pair that off anyway. Rule 3, where's our error? Our error is in this spot right here. And so the answer for this one would be you would just strip this off and leave it, because really the error is in this spot, and it winds up being 2, which is larger than 1. So your answer for this will be B. This is a borderline case, so we would not put this on the exam, but I still want you to understand how it works. Okay, next. Look at that, the same question. 3 decimal places, same average. Standard deviation is 4.3. Rule 1, keep one significant figure if it begins with any number except for 1 or 2. So in this case, we're going to go plus or minus 4. Then this has to match, so it's 32. And then rule 3, you know our error is there. This error is bigger, so our answer for that will be A. Okay. Look at that, another one. Student measured temperature in the room. The thermometer shows 3 decimal places and this average. And our sample standard deviation is 0, right? Well, we already know that rule 1 and 2 really don't apply here. In reality, that this is 0, this is small, we're going to have to go with the instrument error, which is going to be in that place, so it's going to be plus or minus 0.001, so 32.212, 0.001, which will be B. Report the following arithmetic result correctly. Use calculations are provided. Okay, well, let's see. Let's do the math. So first we're going to do this portion here. So it'll be 149 plus 0.334, and we'll add those together. That's right here. And our largest error is in this decimal place, so that will be the answer. So up top we'll have 3 sig figs. Down the bottom will be 3 sig figs. So when we actually do this math here, which is that on the left, we end up having 3 overall, so this whole unit becomes 3. Here we have 4.92 minus 2.158. That's right here. That's going to give us 2.762. Our error is going to be right there at that decimal place, so it's going to be 3 sig figs. So I have all this is 3. This is 3 sig figs, so 3 times 3 will give me 3 sig figs. So there are my 3 sig figs, and it's going to have to be rounded, right? So my answer on this one is going to be D. Okay. Okay, so very similar problem, right? We're going to work the top. We're going to look at these. You can already see that we're adding those together, and that we have these 3 to the right and these 3 to the right. So we're going to have 5 sig figs up top. So up top here, up top will be 5. Down the bottom is 4, right? 5 divided by 4 means this whole term will have 4 sig figs, right? So this whole thing here has 4. Okay, we're going to multiply it by the logarithm of this number. So the logarithm of this number is this. This has 1, 2, 3, 4, 5 sig figs in it. So our answer here will have 1, 2, 3, 4, 5 sig figs. Okay. So 4 times this number, which will actually have 1, 2, 3, 4, 5, 6 decimal places, can only wind up having 4 over here. So the most we can have is 4, because this is going to cut it back. And so your answer for this system will be E. Okay. Report the following arithmetic correctly. Okay, cool. So this is an addition. The best way to do these and solve these problems is look at the answer and look at what the exponent is in the answer and do the math that way. So we have 6.02214 times 10 to the 23rd power. Let's do this one. Well, this is times 10 to the 21st, so we want to be 23rd. So this would go over once, over twice, so it'll be 0.0311416 times 10 to the 23rd. And then lastly, we have this one. And to get to the 23rd, we have to move it over 1 decimal place, so 0.2718 times 10 to the 23rd power. Okay, so this one has 4 decimal places. This has more than 4. This has more than 4. So our answer is going to be, because it's addition, we're limiting it to 4 decimal places. So when we add this together, we're going to get this number, 6, in which case we'll have, well, basically just 4 decimal places, 1, 2, 3, 4, right there. But of course, that 5 will round it up, 6.3254, right? So that will give us our answer, which is C. Likelihood probabilities. So if something has the probability of occurring 68.3% of the time, its probability is 0.683. If something's 95%, it's 0.95. If something's 100%, it's 1. And if something's 25%, it's 0.25. So quite often we talk about probabilities rather than percent. So just so when you see that in the exam, you understand what's going on. So from the Gaussian curve, what is the probability that a result from a population lies between the value of mu and 1 sigma? Well, let's do our, right? So if we're between plus 1 sigma and minus 1 sigma, right? This area would be 64% or 0.64, right? But it's not asking this. It's asking for mu to plus 1 sigma. So just this half of 64%, which would be basically 32%, in which case the answer here is E. From the Gaussian curve, what is the probability the result from a population is greater than 0.1 sigma? Okay, cool. I'm sorry, it's not 64%, it's 68. Ooh, made that mistake. Okay. So we're going to draw the same curve. Ooh, right. We'll put in our 1 sigma and our mu. And remember, in here, that's 68%, which means out here in those two areas must be 100 minus 68, right? So we'll 9, 1, that carry a 2, 32%. So inside those two areas is a total of 32%. But we only want half of it, right? Because this is asking greater than 0.1 sigma. So from here, so here's sigma, up. So it's half of 32, which is going to be 16. So the answer is B. Okay. What would you calculate to determine the magnitude of the standard deviation relative to the mean? Okay. So we want to know something about the standard deviation relative to the mean, right? Or we can write it down like that. And we do have an equation that talks about this, right? Which is the standard deviation divided by the mean times 100, right? And we get that information, right? We call that percent RSD. So standard deviation as a function or relative to the mean. So the answer will be E. A sample of gold was measured 6 times, and the following masses in grams were recorded. What is the value of the median? Okay, so the median is the middle value, and if it's an even number, you have to take the average. Okay, so let's see if we can find the median. So, this is a hunt, right? So let's just write these down. We have 4.47. Okay, these are all 10s, 10 to the negative 3. We have 4.48. Okay, what's the next one? We have 4.52. Okay. We have 4.54. Okay. We have 4.58. Done. And lastly, we have 4.63. So the median is the one in the middle, but because it's an even number, we don't have the one in the middle. So we take the average of the two that are between, and if we took the average of 4.52 and 4.54, we would get 4.53, the number right between them. Okay. You repeat an experiment 5 times and obtain the following results for the concentration of an unknown solution, right? 0.15 molar, 0.14 molar, 0.152 molar, 1.50 molar, 1.48 molar, 1.52 molar, 1.51 molar, 1.50 molar. You're later told that the actual concentration of the solution is 1.34 molar. Select the single statement that is true. Okay, so let's take a look. Are all these numbers grouped close to each other? Well, the answer is yes. They're very close to each other. So we're going to say this has good precision. Now, the average of these, right, 1.52 and 1.51 would average to 1.50. 1.48, 1.50. This would be a little bit below 1.50 would be the average, but the real answer is 1.34. We've missed the target. We're going to say that's poor accuracy. Okay. So your results are precise, not accurate. We are precise and, whoa. How do I get rid of that? There we go. That is true. We are precise and not accurate. So this part is good. We'll look at the second part in a second. Your results are accurate and not precise. No, that is absolutely wrong. Once again, your results are precise, not accurate. Right, we already talked about that at the top. Your results are accurate and not precise. We already talked about that, and B is being wrong. And your results are equally precise and accurate, right? And the error is not significant. Well, they're not equally precise and accurate. So now we're down to 2, okay? Now, your results are dominated by systematic error, or are your results dominated by random error? Remember, systematic error speaks to accuracy. Random error speaks to precision. So where is our problem? We are dominated by poor accuracy. Accuracy is a systematic error because it's in a single direction. So our answer for this one would be A. Awesome. You repeat an experiment 5 times and obtain the following results for the concentration of solution. 1, 1.23, 0.77, 1.17, 0.83. You're later told the actual concentration of this solution is 1.01. Select the single statement that is true. Okay, so we can do a little looking around here. If I were to add 0.83 to 1.17, that sum would be 2.0, which means my average for those would be 1.00. Conversely, I can take these two numbers and add them together to get 2.0, so my average between those two would be 1.0. And lastly, this last measurement is 1.00. So my average for all of these is simply 1.00. Okay? So you're later told the actual version is 1.01 molar. Well, that's pretty good, right? So in this case, we have good accuracy, right? Because our real value is very close to our average value. However, these numbers here, right? These numbers really vary a lot. So we're going to have poor precision. Okay. Whoa. Poor precision. Okay. So your results are precise, not accurate. Well, that is incorrect, right? We already talked about that. Your results are accurate and not precise. That's good. We're already starting on that one. We're good up to here. Your results are precise and not accurate. We already know that's not true. Your results are accurate and not precise. We're good up to there. Your results are equally precise and accurate. That is false also. Okay, because we're looking for the true statement. Okay, your results are dominated by systematic error. So systematic error means accuracy. Your results are dominated by random error, right? This is precision. Where is our error? Our error is in precision, so we are dominated by random error. So our answer for this is D. Okay, in the context of our discussion of error analysis, select all the statements that are false, okay? A given systematic error generally affects the result in the same direction, right? So we know that to be true, right? Systematic errors always go in one direction. So that's a big old true. Okay, random errors can be eliminated completely with careful experimental design. Now you know you can't eliminate random errors. You can just reveal them, right? But you can't eliminate them. They'll always be there. So false. A mistake requires additional testing to determine whether a result can be rejected. Well, if you made a mistake and you spilled something, you saw something break, you don't need additional testing, right? You know a mistake is already bad, and that can be eliminated. Systematic errors reflect the statistical fluctuations associated with a measurement. Systematic errors, right? That's always one direction. This is fluctuation, right? We're talking about random errors. So random errors reflect statistical fluctuations associated with a measurement. So once again, big old false. Lastly, it is straightforward to predict if an experiment will be dominated by systematic or random errors. Absolutely not. You have to do the measurements. There's no real way to predict that. Okay, so the answers for all the false ones would be B, C, D, and E. The sentence below refers to systematic errors. Select all the statements that are false. Okay, personal errors, such as human prejudice and bias, are a type of systematic error. Yeah, if you're always reading the meniscus looking up, you're inducing a systematic error that you will always read this value a little bit lower than it should be. So that's true. Totally true. The probability for systematic errors can be described by a Gaussian curve. No. Random errors are described by the Gaussian curve, not systematic. That's false. Instrument errors, such as faulty calibration, are a type of systematic error. Yeah, if your thing is calibrated 4 degrees too cold in your thermometer, it'll always read 4 degrees too cold and always in that same direction. That's true. Flaws in the design of experiment are a type of systematic error. That is true also, right? If you design experiment incorrectly, where you're always adding too much of a reagent or not enough of a reagent, you will get a systematic error based on it. Just like in experiment 4, maybe you don't add enough peroxide, or you keep the temperature too high, the peroxide won't react to get your iron 3, boom, systematic error. Okay, systematic errors can be revealed or reduced by repetition, right? That's absolutely false. That would be random errors. Right, so our answer for this one will be B and E. Select all false statements about significant figures. The number 5, 6, 8, 9 times 10 to the minus third has 3 significant figures. 1, 2, 3, 4. That's a big old false. Okay, so we're selecting false ones. Okay. The number 210 has 3 significant figures. Correct. 1, 2, 3. The number 5,000 has 4 significant figures. That is a big old false. It has 1 sig fig, right? 5,000 with a period would have 4 sig figs. Okay. The number 0.02000 has 4 significant figures. 1, 2, 3, 4. Remember, zeros to the right after the decimal place have count. So that is absolutely true. The number 34 has 2 sig figs. Yep, also true. Okay, select the correct definition of significant figures. All certain digits and no uncertain digits. No, that is not correct, right? We have to have an uncertain digit there. All certain digits that precede the decimal point. Why would the decimal point have anything to do with it? All certain digits reported on the instrument. Well, by definition, the last number on the instrument is uncertain. All certain digits that follow the decimal point. Once again, the location of the decimal point shouldn't matter. All certain digits plus the first uncertain digit. There's the money. Okay. You measure the pH of your solution 4 times and get the identical result of pH 7.04 each time. How should we report the error? Well, if I were to do that 4 times, right, my average would be 7.04, and my standard deviation would be 0. Okay, so let's see. Report the error as the sample standard deviation, which is S equals 0. Nope, right, you can't have 0 error. We already talked about that, so that's a big old no. Awesome. Report the error as undefined. No, we do have a defined error. If we can't do this, right, we can do the instrument. Report the error as the precision of the instrument. That is absolutely true, but let's continue reading just to make sure that is the best answer. Repeat the experiment until you get a large sample standard deviation. You may not get a large sample standard deviation. You may just continue to get the same number and get that 0. So that is not the correct answer. Lastly, do not report an error. Not going to happen. And yep, we were correct. The answer is C. The pH of a solution is 7.04. The corresponding value for H plus is shown on your calculator as this number. Report this concentration with the correct number of significant figures. Okay, so it wants to know how am I going to take this value to this value and maintain those sig figs. Well, remember, what do we know about pH? pH is the minus log of the proton concentration, right? So this is a logarithm, which means we only have 2 sig figs. That 7 does not count. That means our answer can only have 2 sig figs. 1, 2. 1.1 times 10 to the 7th. Why is it important to report an experimental result with an associated standard deviation? The magnitude of the standard deviation reveals whether the experiment method was reproducible. That's exactly what the standard deviation tells you. So yeah, the bigger the magnitude, the less reproducible it is. The smaller it is, the more reproducible it is. That is a good reason to report it. The standard deviation reveals how close the result is to the theoretical value. No, that's percent error, right? So absolutely not. That is no-go. The standard deviation helps predict the probable result if the experiment were repeated. Exactly, right? You have a 68% chance that the next measurement will be within plus or minus, right? That's standard deviation. So yeah, this is also good. So it would be A and C, and that means the answer is E. Great. In 7L, you will calculate sample standard deviations based on 3 trials. Why do we care about the way we report our standard deviation? With only 3 trials, there is significant uncertainty in the sample standard deviation, right? We talked about that. With 3 trials, we have a 50% error, and we really don't know much about the system. True. Okay. The error cannot be known with high precision given the limited number of trials. Yeah, that is also true. The precision of the result should never be different from that of the standard deviation. The precision of the result. Well, the result doesn't show precision. It's just a number, right? The precision of the result should never be different from that of the standard deviation, right? So that's really not real. So the answer here is going to be some of the above. The image of the burette on the right is shown in class. How many significant figures should be reported in this reading? Well, we've done this many times, right? So this is 30, that's 31. Makes these lines 30.1, 30.2, 30.3. Okay, so 30, it's going to be at least 30, right? And then it's going to be 1, 2, but not 3, so 0.2. So those are all our certain values. So now we put in our uncertain value, which is going to be that one. We'll call it a 5. This gives us 4. So there we go, 4. You perform a multi-step calculation with numerous input values. Select a single statement that is true. After each step, retain all digits as reported by the calculator and round the data at the very end of the multi-step calculation. Absolutely true. But let's read through the rest. After each step, round the data according to the rules for significant figures and decimal places, and use the rounded values as inputs in the next step. No. Every time you round and then do math, you're going to be inducing more and more error. Absolutely not, right? We've already talked about this. You retain all your digits till the very end. Convert the input values such that they have the same number of significant figures. Why would you do that, right? You want to maximize your significant figures and keep which ones you can. Absolutely not true. Do not do that. Convert the input values such that they have the same number of decimal places. That's just as silly as the same number of significant figures, right? The numbers are what they are. We don't ever change those. We just look at the very end and calculate the final significant figures. None of the above. The guidelines for multi-step calculations are unique to each calculation. Not true. We use the same rules all the time. Plus, we have already selected A as being true, and A is the only good answer. There is a very important rule for how a result and its corresponding error should be reported. Select the single statement that is true. The error and the result should have the same number of significant figures. Let's see. 32.4 plus or minus 0.3. That's not the same amount of significant figures, and that number is right, so that can't be right. The error in the right should have the same number of decimal places. Right, 32.4, and this one goes to 0.3. So yeah, it goes to the same decimal place, right? The same decimal places. The error in the result should have the same number of significant figures, which we already know is incorrect, and the same number of decimal places. Absolutely wrong. The error should be reported with greater precision than the result. We already know that's not true. You can't report one with greater precision than the other. The error should be reported with less precision than the result. Equally as absurd. So the answer is B. Right? So here's our error analysis topics, and that should do it. I'll put up some other samples on the web.